All right, so in this lesson, welcome, we are going to look at how to use our algebra skills to find the domain of a logarithmic function. Here we see a graph, and this graph happens to be of a logarithmic function. And like other problems where we have used the graph of a function to find the domain, we can do that for a logarithmic function here as well. Although we're using our algebra today, this will kind of demonstrate one of the possibilities that we get for our domain. So here in this logarithmic function, our argument is x minus 2. I only point that out because the structure of that with x to the first power makes it a linear argument. And when we have a linear argument in our logarithmic function, we end up with a vertical asymptote for the function. And so we notice that our domain, which is our x values, would be the x values that give the points for our curve here. And we know that our curve, as other curves, would have to approach that asymptote but not touch it. So that would mean that the 2 for our asymptote is not part of the domain, but all of the x's over here would be part of the domain, because they would correspond to the x's that are for those points. So our domain here would be, and we want to use set and interval notation. So for our set notation, we would have the set of all x's such that x is greater than 2. So our domain would be all the x values that are greater than the 2, which comes from the asymptote. And then our interval notation, remember, goes least to greatest, so that for the x-axis that would be from left to right, and so that would be from 2 all the way to positive infinity. It is important that you know the difference between your two notations so that when you're asked for only one of them, you give the correct answer, all right, the notation that goes with that particular type of answer, set versus interval. We're not going to be using a graph though today, so that is going to make it important that for our domain, to find our domain, that we have a little clearer understanding of our logarithms, which were introduced in the previous lesson. So remember that a logarithm, which here is shown as log base b of a equals n, that our base is b, that n, remember, represents the exponent value. And logarithms are equal to exponent values always. We learned that in the first lesson. So, and then a is referred to as the argument. In a logarithm, it is required that our argument be a positive number. Positive numbers meaning numbers that are greater than 0. Remember, 0 is not a positive number. 0 isn't positive and it's not negative. It's the only number that does not have a sign. And so positive values for our argument, which is here, is the only way that we can actually say that the math makes sense or the logarithm makes sense. For example, over here, in this first one here, in this little information, the argument is positive. That's our positive 9. The exponential form of this, remember this logarithm is equal to some exponent. I'm going to call that y, so I have 3 to the power of y equals 9. Well, that makes sense because I know that 9 is 3 squared. So that tells me that my y value, or my logarithm, has a value of 2. So this is defined when my argument is positive. If my argument here in the second case is 0, then this is equal to some exponent. I'm saying 3 to some exponent must be equal to 0. But if you recall, if y is a positive number, 1, 2, 3, so on and so forth, you're going to get numbers bigger than 1. If y is equal to 0, remember that would be equal to 1. Anything to the 0 power is 1, so that doesn't work. And remember, if y is a negative number, that doesn't produce 0 either. That produces ratios, fractional powers. That would be 1/3 if I had an exponent of -1. So there's no way that a power can equal to 0, which is our argument value. So when the argument is 0, the logarithm is not defined. If the argument is negative, that's our -1 here. Remember, that's not your exponent. You're equal to your exponent. So 3 to some exponent equals that argument, which is -1. This isn't possible either, for the reasons that I just outlined before. If y is a positive number, we get positive powers. If y is 0, we get 1. If y is a negative number, we don't get negative numbers, we get positive fractional powers. And so this logarithm is not defined. So the only time we get a defined logarithm is when our argument is positive. That's going to be important for understanding why the algebra begins as it does. So when we are going to find the domain of a logarithmic function using our algebra skills, our independent variable, such as x, is going to be part of the argument. Therefore, we will set up an inequality that sets the argument greater than 0, which is representing positive numbers. So that creates an inequality, and then we will solve that inequality. Now, here's where things will get different between one problem and the next. In this lesson, our arguments are going to be either linear expressions or quadratic expressions, which will create then either a linear inequality or a quadratic inequality. If we are solving a linear inequality, we will use our basic undoing algebra, that's the reverse order of operations, with the exception that if we, in our algebra, have to multiply or divide both sides by a negative number, then we must change that inequality symbol from greater than to less than. If we are solving a quadratic inequality, you have to remember that you can't use your reverse order of operations. It doesn't work because a quadratic inequality will have more than one value that makes it equal to 0. And these we actually create a number line with intervals. And we test those intervals to determine if they're positive or negative values. For these problems, we will see that we will need the positive intervals because greater than 0 means positive. But you will have to, that's the only way it will work, and the only way you can justify your final conclusion is by following that procedure with a quadratic inequality. All right, let's take a look at this first example. So here we are finding the domain of the function, which is a logarithmic function. Does not matter what base your logarithm is. Here it's a base 10, our common logarithm that we learned about in lesson 1. But all logarithms, the argument has to be positive. We'll use both set and interval notation when we're done. It is important that we can recognize the argument. Remember, the argument follows the logarithm. So it is the expression here in our parentheses. That is our argument. And by definition, the argument of any logarithm must be positive, meaning it must be greater than 0. So our argument is 9 minus x in this function. So 9 minus x must be greater than 0, positive. Now, 9 minus x is linear because x is to the first power. So I am going to just use my basic undoing algebra. Now I have a couple of options here. I can start by subtracting 9 from both sides, or I can start by adding x to both sides. I'm going to do this one both ways, just so you can see and everybody is clear what is happening with the algebra. And it doesn't, then you can choose whichever method you like best when you're doing a problem on your own. So this first one, I'm going to start by undoing the positive 9. So I'm going to subtract 9 from both sides. This will give me negative x, and subtraction does not change my inequality symbol, so it would still be greater than. But now I'm going to have to undo this negative 1 by dividing both sides by negative 1. And with an inequality of this type, when I divide both sides by a negative, that does require me to change the symbol. So my greater than becomes less than, and I get x's must be less than 9. With this other option, the other option is I could start by adding x to both sides. So I could do this. And now what I have is 9 is greater than x. But you need to realize that this is not a final form for an inequality. In our set notation, it's required that our x be first. And if I have to rewrite it so my x is first, this is going to require me to change my symbol so that it means the same thing. In blue here, it means 9 is greater than my x values. Well, that is the same as x being less than the number 9. And so that, now that you'll see that they turn out to be exactly the same. And so then we have our set notation, which would be the set of all x's such that x is less than 9. And then our interval notation, which would, again, and it's can be helpful here if you don't know your less than, greater than symbols, which one is which real clearly. This can be a little harder than it's supposed to be at times. Being the less than symbol, that would mean that I'm looking at numbers over here. So from least to greatest for my interval notation, that would start at negative infinity and go to 9. So as I was saying, if you have some trouble with less than, greater than, and being confident about which one's which, what I was taught when these were introduced to me is that the less than symbol looks a lot like our letter L, our capital letter L, and the word less starts with L. So that's how I know that that one is less than. So then if it goes the opposite direction from an L, then I know that is going to be greater than. And that might help some of you who are still having trouble with that. Some other things to keep in mind, you can actually test your algebra to make sure that in general it makes sense. Like if you decide your x values must be less than 9, then if you plug in 9, you should get 0 for your argument, which I do. 9 minus 9 is 0. And if you plug in a number less than 9, like 8, then you should get a positive number. And 9 minus 8 is positive 1. So it just kind of quickly verifies that my domain is making sense according to this definition, that the argument has to be greater than 0. All right, so here we have our logarithm function. This is a natural logarithm. That's our ln symbol right there, which means a logarithm base e. But again, it doesn't matter what kind of logarithm we have. The domain of a logarithm function is always defined by the argument being positive, because our independent variable of x is going to be part of that argument. So if our argument here would be the 4x plus 7, because that is what we are taking the logarithm of, the quantity in parentheses. So that 4x plus 7 must be positive, meaning greater than 0. Now, 4x plus 7 is again linear because x is to the first power. So I'm again going to use my basic undoing algebra, reverse order of operations. This one I would probably only do one way, so I'm just going to go ahead and just do it that way. So I'm going to subtract 7, undoing that addition first. Subtraction and addition never change the direction of the symbol, so it's still greater than. Here I would now undo the multiplication, dividing by sides by 4. Since 4 is positive, I'm dividing by a positive number. That does not change my symbol, so it remains greater than. And negative 7/4 is, I'm just going to leave it negative 7/4. It can't reduce. And these are technically no calculator problems, so I would not bother with a decimal in this case. So I'm looking at then, for my set notation, it would simply be the set of all x's, such that x is greater than negative 7/4. And again, this is your greater than symbol. So if you were to look at this on a number line, it would be numbers to the right of negative 7/4, which means our interval notation, which has to go least to greatest, would go from that negative 7/4 to infinity. This example also serves to show that your value, like your negative 7/4, can be a negative number. It can be a fraction. So you can have any number here in a linear inequality, any real number in a linear inequality. And just so long as, you've verified your algebra is correct, it's good to go. All right, so in this third example, we are going to get into a situation or a problem where our argument is a quadratic, which means, remember, the highest power of x is 2x squared. So the definition of an argument for a logarithm is that it has to be positive, regardless of what kind of logarithm you're working with, regardless of what the argument looks like as far as what kind of expression it is involving x. That must be a positive value. So that argument of 64 minus x squared must be positive, meaning greater than 0. Here's where the algebra will be different, because being a quadratic inequality, you cannot use your basic undoing algebra in the inequality. All right, you can't add x squared, take the square root, and have, x plus or minus 8 with greater than, less than. That's not how a quadratic inequality works. What happens with a quadratic inequality, this is kind of a two-step process here. The first step is to figure out where the expression of 64 minus x squared would be equal to 0. Now, when you're doing this, you can use your basic undoing algebra with an equal sign. You cannot use it with an inequality symbol. So here I can add x squared to both sides and then take my square root. Remember, with the square root property, you're going to have to include that plus minus. So this is going to give me two x values, negative 8 and 8. These x values are what define and create our intervals on our number line. So this number line is our second step, and this is required work for a quadratic inequality. This number line here is representing our x-axis, and remember, our domain is x values. So we're looking at this x-axis being divided into 3 sections or intervals by the negative 8 and the positive 8. And make sure, of course, that the smaller number is to the left, so your number line makes sense. We now have to test these intervals to determine if the x's in each of these 3 sections will create positive values when plugged into 64 minus x squared, or negative values when plugged into 64 minus x squared. We can do that in a couple of different ways. One, we can literally do that with numbers. For example, I can choose x to be 0, which would be between the negative 8 and the 8. So I'm looking at 64 minus 0 squared, which is 64 minus 0, which is 64. 64 is a positive number. So that means that the x's in this section will create positive numbers. Remember, I want my argument, which is 64 minus x squared, to be positive, to be greater than 0. That means that this section is part of my domain. Now, you might recall, and this depends again on we've always got options, but if you recall that a quadratic alternates positive and negative intervals, then you would know, okay, well, that means that this section would have to create negative numbers, and so would this section. So they would not be part of our domain, because we don't want negative numbers for 64 minus x squared, which is our argument. We want positive. Now, if you're not confident about that, you can test all of these intervals, or as many as you need to until you're confident. For example, over here on the far right, I can pick any number that's bigger than 8 as a test number, such as 9. So now I'm looking at what is 64 minus 9 squared. Well, that's 64 minus 81. Smaller number minus bigger number is negative. In this case, I think it's negative 17. So again, I don't want negative numbers for my argument, so this cannot be part of my domain. Over here on this left section, I could pick a number such as negative 9. Now I'm looking at 64 minus negative 9 squared, which also gives me 64 minus 81, which is negative 17. So again, that's a way to verify that, okay, yeah, that section not going to be part of our domain values. Only the middle section is. Now, that's using your basic math. And your basic math, like if I'm testing, that's required. Justify positive and negative with some basic math. Always show that basic math as part of your work. The other way, as some of you might recall, is to look at it graphically. And by it, I mean 64 minus x squared. Look at this as a function, y equals negative x squared plus 64, which graphs as a parabola. So look at this graph. Now, this graph has an a value of negative 1. When a is negative, remember, that means there's an x-axis reflection. That means the parabola is going to open down. The parabola will have zeros of negative 8 and 8. So the parabola crosses the x-axis at negative 8 and opens down. Well, notice that the parts of the parabola that are below the x-axis correspond to negative y's. And the part of the parabola that's above the x-axis corresponds to these positive y's. So either way, it's justification for concluding that this section of x's is our domain. So now I'm going to write my domain in my two notations. My set notation, now, we've done this before, but it's been a while. Set of all x is such that this section, this interval, is bounded by two real numbers. That creates what we call a compound inequality that is written negative 8 is less than x, and x is less than 8. Notice both symbols are less than symbols, and they have to be for the math to make sense, because this is saying that our x's are greater than negative 8, and our x's are also less than positive 8. For our interval notation, we've only got one interval in our domain, and it starts at a low of negative 8 and goes to positive 8. We use parentheses because the negative 8 and 8 are not included. And remember, that's because the negative 8 and the positive 8 are actually what make our argument equal to 0. And we cannot have an argument equal to 0. We have to have an argument that is greater than 0. So these numbers at the ends of our intervals will never be part of our domain. So that finishes up this problem. All right, let's take a look at the next one. So here, dealing with another quadratic argument. So x in general, the argument is always positive. So this creates a quadratic inequality, which means that we have to go through that process of figuring out where is the argument equal to 0, because those numbers are going to separate and define our intervals on our number line, which represents our x-axis for our domain. So I would add 20 to both sides, then use my square root property, giving me plus or minus the square root of 20. Now, for this, on my number line, I'm going to go ahead and use positive and negative square root of 20. But in my domain and my final answer, I'm going to use the simplified form of positive and negative 2 root 5. But over here, I'm just going to use negative square root of 20 and positive square root of 20. And I'm going to show you why here in a minute. So for those of you who like to use your basic math and plug in numbers to test your intervals, you can do that in one or more of these intervals once you get the kind of the pattern that goes with it. So for example, let's say that you want to test a number over here on the far right interval. So these are the numbers greater than the square root of 20. You can pick any number you want to. So I can, and you remember these are no calculator problems, so we don't really know a decimal value per se for square root of 20. So all I need to do is pick a square root of a number that's bigger than 20. Pick the square root of a number where the number is larger than 20, like 25. What is the square root of 25? It is 5. And use that number, and that will guarantee that it's in this section or interval. So remember, our argument is x squared minus 25. So I'm looking at 5 squared minus 20. That's 25 minus 20, which is 5. Oh, well, 5 is greater than 0. It's positive. That means this section is going to be part of my domain. And this is my work to justify that. Now again, you might remember that you've got alternating intervals, and that's good. But if not, and you're not sure, you can test as many of your intervals using your basic math as you want to. Remember, between any negative and positive number, 0 is always going to be there. So for the middle one, I can test 0, which will give me 0 squared minus 20, which is 0 minus 20, and oh, that's negative 20, not positive. It's less than 0, or not greater than 0. So this section is not part of my domain because it creates negative numbers. Can't have a negative argument. And then I could repeat that process over here. If I wanted to test something over here, I need to pick a negative square root of a number bigger than 20. So like negative square root of 25, which would be negative 5. And then I'm doing negative 5 squared minus 20. Oh, look, that's 25 minus 20, which is 5, which is greater than 0. So this section is also going to create positive numbers, so it is part of my domain. For those of you who like that graphical method of showing your work to justify your domain, what you'd be looking at is the graph of the function y equals x squared minus 20. So this is a parabola. It's quadratic, so it's a parabola. Its a value is positive 1, so there's no x-axis reflection, which means that the parabola opens up and crosses the x-axis at negative root 20 and positive root 20. So the parabola would look like this. Oh, look. This section over here that's above the x-axis corresponds to positive, which makes sense. This section, which is above the x-axis, corresponds to positive, which makes sense. And the section that is below the x-axis in the middle corresponds to negative, which makes sense. So that gives me the same result if I understand how to interpret the graph of that parabola. So, for the domain in the set notation. Now, notice this time we have 2 intervals. That's going to give us 2 separate inequalities. So we have the set of all x's such that this one over here on the left is numbers to the left of negative 2 root 5. So that's less. So we have x's less than negative 2 root 5. Or the one over on the right, which are numbers to the right of positive 2 root 5, would be x's greater than 2 root 5. Interval notation. Well, we have 2 intervals, remember. 2 inequalities, 2 intervals. So this one over on the left, negative infinity to negative 2 root 5. And remember that would be in union with the other one, which starts at positive 2 root 5 and goes all the way to the right, which is positive infinity. There's both our notations for our domain. All right, in this next example, we again have a quadratic argument. The argument would be what we're taking the logarithm of, which is inside our parentheses. So in the previous 2, our quadratic argument was a binomial of x squared minus a number minus x squared, which allowed us to use the square root property to figure out where it was equal to 0. Here, we can't use that because we have a trinomial structure. So we start off with the concept that our argument, represented by the trinomial, must be positive, meaning it must be greater than 0. And to solve this quadratic inequality, procedure is exactly the same. We start by figuring out what the numbers are that are going to create our intervals or define our intervals by figuring out where this quadratic equals 0. Now, because this is a trinomial, we cannot use our square root property, but so instead we look at factoring, and if factoring doesn't work, we could look to our quadratic formula. Here, factoring does work, but something interesting happens with this particular trinomial. The binomials that we get are the same. They're both x plus 5. And so our zero product property gives us one x value that's repeated, an x value of -5. So when I go to create my intervals on my little number line, which represents my x-axis for my domain, I've only got one number, so it actually only creates 2 intervals. So this is why this one is a little bit different and why we're looking at it specifically as an example. So what do we do if we only have 2 intervals? Well, we can use both strategies. We can use our algebra, or basic math rather, with testing each interval, or we can use a graphical strategy of figuring out where our domain is. We'll start with just testing our intervals using our basic math. So I want to test each of these. So I want to pick a number that is, say, smaller than -5, like -6, and plug that in. And I can actually use, if you notice, you can use this, or you can use the factored form, which is x plus 5 quantity squared, because we have x plus 5 times x plus 5. You can use either one. So you can go -6 squared plus 10 times -6 plus 25, or you can do -6 plus 5 quantity squared. Well, the second one is definitely easier if you realize if you think of that as a factored form, but they both will give the same result. This gives 36 plus -60 plus 25, and this gives -1 squared. Both of them actually end up giving you 1, which, well, 1 is a positive number. So that means this section is part of our domain. And remember, this is your work to justify the conclusion that this is part of your domain. On the other side of the -5, I would have numbers bigger than -5, like -4. And so I could again do this either way. I could do it -4 squared plus 10 times -4 plus 25, or I could just do -4 plus 5 quantity squared. Either way. Either way, here I get 1 squared, here I'm going to get 16 plus a -40 plus 25, which is 1. And so it's again positive, which means that this section also creates positive values. So it must be part of our domain. So careful here, because now some people mistakenly think this means that our domain is the set of all real numbers. It is not quite the set of all real numbers, because remember, -5 cannot be part of our domain. Because if we plug in -5, our argument is equal to 0. And we can't have an argument that equals 0. So we do have 2 intervals here for our domain, 2 separate intervals that are divided from each other by the number -5. So when I go to write my domain in set notation, it is going to look like this one, except I'm going to have -5 as both of my numbers. So I have the set of all x's such that my x's must be less than -5, or my x's must be greater than -5. And for my interval notation, my first interval, my leftmost interval, would be from -infinity to -5, non-inclusive, meaning not including -5, in union with from -5 to infinity, non-inclusive of the -5. And that finishes up that one. So that's, if you end up with only one x value, you will create 2 intervals, 2 sections, and that creates that. Now, let's go back to the other strategy, for those of you who like that graphical strategy of determining your domain. So we would be looking at the graph of y equals x squared plus 10x plus 25, which in its factored form is y equals x plus 5 quantity squared. So from what we learned about graphing parabolas, our a value is this positive 1, so there's no x-axis reflection, meaning our parabola opens up. And our vertex, which is h comma k, would be negative 5 comma 0. So what this is saying is that our vertex is right here, and our parabola opens up, like so. Oh, well look, this section on the left is above the x-axis, corresponding to positive numbers. The section on the right is above, corresponding to those positive numbers. And our vertex, which is on the x-axis, means that that x value of negative 5 is not positive, or is not corresponding to a positive number. It corresponds to a y of 0, so it can't be part of our domain. So that you could do it that way also. All right, got one final example. And then we should have everything, an example for, kind of to refer to for everything that we will be seeing in this assignment. So again, it doesn't matter what kind of logarithm we have. All logarithms, the argument must be positive. And the argument here would be what we're taking the logarithm of x squared plus 16. So this again creates a quadratic inequality. So that process for solving a quadratic inequality begins by figuring out how our intervals are separated from one another, which is by the numbers that create us this x squared plus 16 being equal to 0. And then we can figure out our separation of intervals on this number line, which represents our x-axis for our domain. So going back here to solving this, so we would undo the subtraction, which would give us x squared, or undo the addition with subtraction, which would give us x squared equals negative 16. Take the square root of both sides. And remember, this would give us plus or minus the square root of this number, which is a negative 16. So hopefully you remember that the square root of a negative number is imaginary. And in this case, we would get positive and negative for I. So what does this mean about our intervals? Remember that this number line represents our x-axis, and there are no imaginary numbers on the x-axis. So what this is telling us is that imaginary numbers will make this equal to 0. So, and there are no imaginary numbers here. So that is telling us then that, oh, okay, well then our domain is going to be all of these. We don't have to exclude anything, which is the set of all real numbers. For those of you who like the graphical way of doing this too and seeing the graph, if you look at the graph of y equals x squared plus 16, this is a parabola that opens up because a is positive and has its vertex h comma k at 0, 16, which remember would be on the y-axis right there. So here's your parabola. Notice that it's all above the x-axis. So everything is positive. And that means all x's create positive values. So all x's are in the domain, all real number x's. So now when I go to write my domain as a set, the set of all real numbers, remember, in its set notation would go from negative infinity to infinity. So the inequality looks like this, not that one, this one, where you have that compound inequality bounded by the numbers on the ends, except instead of numbers on the ends, we're bounded by our infinities. So set of all x is such that negative infinity is less than x, and x is less than infinity. And our interval notation goes from negative infinity to infinity, like so. So logarithm functions are kind of interesting, especially when you have a quadratic argument expression. You can have several different options. Sometimes you might end up with a domain of the set of all real numbers, like here. Sometimes you might end up with only 2 intervals. and sometimes you'll end up with 3, where the outside intervals are the domain, and sometimes the inside interval is the domain. All right, that does finish everything up here for this lesson.